Hi everyone, welcome to episode 2 of Rope Shenanigans, and I am definitely not Richard Delaney. Per Zach's request, I'm going to be doing a video on rope rescue physics. Primarily, we're going to be talking about anchor forces and redirection forces, so high directionals and that kind of thing. At the end of the day, it's fairly simple. Yes, there are a lot of variables involved, but we can use some rules of thumb to kind of calculate things on the fly. So, without further ado, let's take to the tablet and get right into it.
All right. Hi, everyone. Definitely not future Ben here, having definitely not forgotten to include learning objectives in this presentation. So before we dive into the tablet, we're going to talk learning objectives. Okay? What do I hope for you to learn throughout the course of this presentation? And those are, you should be able to understand force as a concept. You should be able to understand the kilonewton as a unit of measure, right? What is it? Why do we care about it? And you should be able to understand the basics of vectors, right? What are they? How do they connect to this whole thing? And we're going to get into that. You should be able to understand, calculate, and apply information regarding forces at the load and at the anchor, right? A single point anchor. You should be able to understand, calculate, and apply information regarding forces on multi-point anchors of various types. And you should be able to understand, calculate, and apply information regarding forces on redirections, such as high directionals and that kind of thing. So, now let's get into the tablet and talk physics. I'll see you there. All right, so I apologize in advance. There's going to be a lot of math here. There's going to be a lot of numbers, a lot of angles, a lot of trigonometry. Just bear with me here. This is all important. It's kind of like anatomy and physiology and pathophys and pharm on the medical side, right? The more you know, the more you can do. So let's get into it. So 1 pound equals 0.4536 kilograms, or 1 kilogram equals 2.205 pounds. We generally calculate that as 2.2 just by rounding. To get your calculation, it's going to be pounds divided by 2.2, close enough. Or if you want to calculate it on the fly, right, this is my kind of 3 a.m. Pounds to kilograms conversion. Pounds divided by 2 minus 10% equals kilograms-ish. So before we get into the whole force side of things, I want to point out that gravity is a constant at 9.81 meters per second squared. So in a vacuum, right, in the absence of any air resistance, everything falls at 9.81 meters per second. So the formula for force, this is very important, is mass times acceleration. When I'm just standing on the ground, that is 9.81 meters per second. 9.81 meters per second squared, okay? Static force, right? This is how we're calculating weight, essentially. I weigh 158 pounds. That's 71.7 kilograms. So to get from kilograms to kilonewtons, we're going to multiply that, assuming I'm static, assuming I'm not moving. We'll get to that in a second. We're going to multiply 71.7 times 9.81. That gives us 703.4 newtons, or rounded 0.7 kilonewtons static. Okay? If I'm moving, we have to add that acceleration, that movement, to our calculation of force. Okay, that's why fall factor is so important, right? The faster you're falling, the force you generate is going to rapidly increase. All right, moving right along, let's talk about forces on redirects. Okay, so imagine at our origin point right here, this is our pulley, right? This is our high directional, whatever you want it to be. Okay, and our rope is going from our anchor to our load. At 180 degrees, a straight line, there is zero force on our redirect because it's essentially just kind of passing through the pulley, tangent to the pulley for my math folks out there. Okay. At 150 degrees, it's half. Okay, so let's say we have a load of 1 kilonewton. We'd have 0.5 kilonewtons pulling on our redirect. At 120 degrees, it is 1 times whatever our load is. Okay, so 1 kilonewton, we have 1 kilonewton pulling on our redirect at 120 degrees. The reason for this is we've essentially created 2 equilateral triangles, as we talked about in Rope Shenanigans episode 1. At 90 degrees, so anything less than 120 degrees, we're multiplying our force on our redirect. So at 90 degrees, it's 1.41. At 60 degrees, it's 1.73. At 45, it's 1.85. At 30, it's 1.93. And at 0 degrees, it is twice the load. So if we have a 1 kilonewton load and it's going up into a pulley and coming right back down, in an ideal world, assuming the pulley is 100% efficient, yada, 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 you would have 2 kilonewtons pulling on that redirect. So TLDR, the shallower your angle in your redirect, right, the closer your ropes are together, the higher the force is going to be on that redirect. So let's practice this. Let's see how this works out. Okay. Again, we're going to assume that our pulley is 100% efficient because less variables is going to simplify this a little bit. And let's say that we have a 90-degree angle between our anchor and our load running through our pulley. So if we go back to our kind of chart that we had, that would be 1.41 times the load. So if let's say we have a 1 kilonewton load, we're going to multiply that by 1.41, giving us 1.41 kilonewtons at our redirect. Now, which direction is our pulley being pulled? Okay, that's what we call our resultant force, and we're going to get into that in probably more detail than any of you would like here in a moment, but it is worth noting. Is it the direction that the pulley is going? Not necessarily. That is a general rule of thumb that we can use. You can look at the direction that the body of the pulley is going to kind of rule of thumb guess your resultant force. But we're going to get into how we actually calculate that in a moment and why resultant force is important. So let's do yet even more math, shall we? All right. Before anybody freaks out and turns the video off, yes, there's a lot of numbers here. There's a lot of math here, but it's important to understand the basics here. Okay. How do we figure out what this resultant force is? Okay. And more importantly, when we're dealing with high directionals and tripods or gin poles or things like that, how do we figure out which way that high directional is being pulled? Okay, that's important, right? Because let's say instead of this being these green lines being 2 ropes, let's say this is we have legs of a tripod here, right? We need to calculate that resultant force to make sure that it is not outside of the tripod, so we're pulling inside a nice stable base. Or let's say we're using a gin pole, we need to calculate the resultant force of whatever we're using to secure that gin pole so that we're pulling appropriately on those anchors. Okay, now how do we do that? We have 4 vectors here. Okay, a vector is essentially a line that has a length and a direction. Okay, yes, it's not a line for my geometry people out there. It is a vector, 2 different things, but it is a straight section that has both direction and length, magnitude. Okay, so we're going to consider our rope going to our anchor, from our anchor to our pulley, and from our pulley to our load to be the 2 vectors that we're calculating. And we can actually break that down into 4 vectors, which, believe it or not, makes it a little bit simpler in the end. We have our vector on the x-axis of A. We're going to call this A. We're going to call this B. We have our vector on the y-axis of A. We have our vector on the x-axis of B and our vector on the y-axis of B. On the x-axis, A is going to be negative 0.866 and B is going to be 0.5. Okay, we're assuming a 90-degree angle here, and we've already done some math to calculate what these side lengths are. Okay, just basic geometry stuff. On the y-axis, A is going to be 0.5 and B is going to be 0.86. Okay, and that's largely the result of the difference in angles here. So, slope, if you want to go back to basic geometry, is rise over run, or delta y over delta x. So we're going to add our y components and our x components, okay? 0.5 plus 0.866 equals 1.366. That's our net force in y. And then absolute value of negative 0.866 plus 0.5 equals 0.366, right? Absolute value, we take that negative, we turn it into a positive, good to go. So net force on the x-axis is 0.366, and we can calculate our slope, which is rise, 1.366 over runs, 0.366, giving us 3.73. And we can use that to calculate our angle, which is the tangent to the minus 1 of our slope, and that gives us 75 degrees, and that is relative to the origin. So relative to the x-axis, 75 degrees, so this would be our resultant force. When we apply this in real life, right, you can kind of look at how much tension is being applied to various anchors if you're using a gin pole, but it is important to note, like let's say you're using a tripod or a bipod, you want to take a look and see which way that's actually being pulled, so you're using that equipment appropriately. But this is the why behind all of that. Now, I'm not going to dive too deep into anchors right now, primarily because if you go back to Rope Shenanigans episode 1, most of that content is in there when we talked about the span anchor. All of that math that we did on the span anchor, you can apply to any 2-point anchor. And if you want to get real complicated, you can do the same thing and just include some more numbers and do the same thing for a 3-point anchor. So I think that is enough math for one day. So I leave you with Rope Shenanigans episode 2. Episode 3 coming soon.